All right, so last class period we finished out chapter 15, our discussion of aromaticity, and we talked about a few reactions of our benzene derivatives, specifically that happen at that benzylic position. Now we're going to talk about a different class of reactions that our benzene derivatives undergo, what is called electrophilic aromatic substitution reactions, or EAS. Right? So these are reactions that take place between benzene and an electrophile. All right, and what I'm going to do first is we're going to look at the generic reaction mechanism. And then we'll start looking at specific electrophiles. But right now we're just going to do benzene reacting with some generic electrophile, which we're going to use the symbol E+ for. Okay. What we're going to also do is we're going to put in these implied hydrogens to make it a little easier to see what's going on in this mechanism here. All right, so about one of those double bonds, I've put in my implied hydrogens. Of course, they all have one hydrogen on them, but just those in particular to see. And similar to alkenes, benzene is going to be playing the role of the nucleophile in this reaction, because not surprisingly, the electrophile is going to play the role of the electrophile. All right? So benzene, just like we saw for our alkenes, benzene and in particular this pi bond pair of electrons right here is going to play the role of the nucleophile. My electrophile here is, of course, playing the role of the electrophile. And what do nucleophiles do to electrophiles? Attack. All right, nucleophiles attack electrophiles. That's what we see over and over and over again, right? Nucleophiles have a lot of electron density. That electron density reaches out and attacks an electrophile. All right, so we're going to practice our mechanisms quite a bit today. Importantly, you're going to draw me my intermediate here. Is this a bond breaking arrow, a bond formation arrow, or both breaking and formation? It's going to be both, right? So we're starting out at a pair of bonding electrons, but it's also forming this new bond with our electrophile. So this is both breaking and formation. All right, we looked at these a lot when we were doing our reaction mechanisms for conjugated dienes as well. All right, and when we have these bond breaking and formation arrows, starting at our pi bonds, what we see is that one of these carbons gets that new bond, in this case my carbon electrophile bond. Since my electrophile started as being positively charged, when it accepts that pair of electrons, it's going to be neutral. All right, and then what else am I missing in my intermediate here? Yeah, one of those carbons gets the new bond. The other one just straight up got that pair of electrons taken away from it. And we drew this explicit hydrogen in here, or rather implicit hydrogen in here explicitly just to show this only has 1, 2, 3 bonds now. So 3 bonds, no lone pairs. That's our bonding pattern of our carbocation. Again, very common consequence that we see from these bond breaking and formation arrows. All right, so at this point we've added on that electrophile, right? But benzene does not like to undergo addition reactions because it starts out with this nice, super stable conjugated ring, right? And in order to do this step right here, we had to break that conjugation. So it's not really happy right now. And it wants in this next step to reform that conjugated ring so it gets its aromaticity back. So what happens is in our next step, our base, usually played by our solvent, is going to accept this hydrogen. We're going to get a proton transfer. And importantly, that's going to allow this pair of electrons to come back down and reform that pi bond. All right, so we've managed to keep our aromaticity in this reaction. We broke it at first, but then we reformed it. And now we have our electrophile attached to that ring. All right, so an electrophilic aromatic substitution reaction. Electrophilic because we have to react benzene with some electrophile. Benzene's going to be playing the role of the nucleophile, so we need something relatively electron deficient. Aromatic because we're starting with that aromatic ring. We're also ending with that aromatic ring. And substitution, this isn't an addition reaction, but rather we're substituting a hydrogen from that benzene ring for whatever our electrophile is. All right, these are our electrophilic aromatic substitution reactions. All right, so again, this was kind of our generic reaction mechanism. Now we're going to take a look at a few specific electrophiles that we can use. And what we're going to do is we're going to create this little wheel here that's going to help us summarize these different reactions. All right, we're going to have 6 different electrophilic aromatic substitution reactions. So what we're going to do is we're going to make a little wheel with these 6 arrows coming off of it. And this is where we'll kind of summarize each one of these reactions, and then we'll talk a little bit more specifically about each one as well. All right, but this is more or less our cheat sheet here for these 6 reactions that we're going to learn. Okay, and in each case, again, we're substituting a hydrogen on that benzene ring for something else. So I'm going to just show one of those hydrogens explicitly. All right, so our first reaction here is going to be using bromine. Okay, and what we're going to create is bromobenzene. So we're swapping out a hydrogen for a bromine. Okay, but importantly, what we're going to see is that these reactions always need some sort of a catalyst. It turns out that benzene, which is playing the role of the nucleophile, is a pretty crappy nucleophile, right? Because those electrons are pent up in that aromatic structure. So they're not really dying to be donated to some electrophile. So in order for these reactions to occur, we need a really good electrophile, something that's really good at accepting electrons. So we're always going to have some catalyst as well. And in the case of this reaction, you can actually choose one of 2. They're very similar, either aluminum bromide or iron 3 bromide. All right, we're actually going to knock 2 of them out real quick because the next one is very, very similar. If instead of using bromine, we used chlorine and aluminum chloride or iron 3 chloride, what is that going to add to my ring? A chlorine. So not a bromine atom, but a chlorine atom. All right, right, so we can add a halogen to our ring, or rather substitute a hydrogen for a halogen on our ring using these two reactions here. These are called halogenation reactions. We're going to look a little bit more closely at them. We're going to save some room because we're going to go back and fill in the rest of this wheel. But now we're going to go talk a little bit about each of these reactions. So let's talk about our halogenation reactions. All right. I'm going to look specifically at our bromine one, but the chlorine one's exact analogy, just replace all the Brs with Cls. So again, bromine and some catalyst. Let's look at aluminum bromine. And again, we're going to substitute that hydrogen for bromine on that ring. Okay? So this is like step one when we're learning our reactions. We want to know what our substrate reagent product combination is, right? Our substrate's going to be benzene for these reactions, these aromatic compounds. So really the trick is you need to be able to look at this set of reagents right here and know what you're supposed to be putting on that ring, right? In this reaction here, this set of reagents is what puts a bromine in place of a hydrogen on that ring. So that's step one, all right? Then we can look more specifically at our reaction mechanism, but what we need to know is what our electrophilic species is in this reaction. It's not just the Br2 all by itself, but it's going to involve that catalyst. Bromine by itself will not react with benzene. You have to have that catalyst in there. Okay? And that's because this catalyst forms this complex with our bromine, and that's what's actually involved in our reaction, what we would call our electrophilic species. All right, so what happens is our bromine, diatomic bromine, right, Br2, it will react with this aluminum bromide. All right, aluminum's a little weird because we classify it as a metal, but it's got some metalloidy behavior to it, where it can play the role of a Lewis acid and accept this pair of electrons from this bromine. All right, so everybody's going to take a second and follow these electron pushing arrows. Show me what my next step is here. Is it bond breaking, bond formation, or both? Right? Use that to figure out what you're supposed to be drawing on your product side here. All right, so what one was it? Breaking, formation, or both? So I'm starting at a lone pair, reaching out over here, so this would be a formation arrow. So all I need to do is add a new bond between my bromine and my aluminum. All right, putting in my lone pairs here. We're missing some formal charges. This bromine in the middle here has 2 bonds and 2 lone pairs. So does it have a positive or negative formal charge? If I swap out a lone pair for a bond, does that increase or decrease my formal charge? So I'll give a positive formal charge. keep everything neutral, right? It turns out, and I wouldn't really expect you to know this because we didn't talk about the bonding patterns of aluminum, but you can convince yourself that it accepts this extra pair of electrons right here when it is neutral. It's going to get a negative charge. And this complex right here is what we call our electrophilic species. Meaning it is the actual electrophile in our reaction. Okay, so if we wanted to do our reaction mechanism here, we would take our benzene and we would react it with our electrophilic species for this reaction. All right, so again, benzene is going to play the role of the nucleophile. It's going to grab this bromine right here, and that positively charged bromine can easily accept that pair of electrons. Okay, that's how we get our carbocation intermediate. Where on one carbon we have our bromine attached, and on the other carbon we get a positive charge. All right, now since importantly the hydrogen on this carbon is also involved in our next step, I'm going to draw that in, and I'm going to show some base, again, usually our solvent. Deprotonating that carbocation intermediate, allowing for our benzene ring to reform, now with that bromine in place of that hydrogen. So here would be our mechanism using that specific electrophilic species for this reaction. All right, so these are our halogenation reactions. Again, we can use chlorine or bromine. If you wanted to do the same electrophilic species and reaction mechanism for chlorine, you would just replace all your CLs, all your BRs with CL, same thing. All right, but that would allow us to add a halogen to that ring in place of our hydrogen, or rather substitute a halogen for our hydrogen. All right, so the next reaction is what's called a nitration reaction. So this is going to use nitric acid, HNO3, and we need a catalyst, sulfuric acid. And this is going to add one of those new functional groups we introduced last chapter, a nitro group, NO2, to the ring. Okay, so again, this is what we call a nitration reaction. Let's do our substrate, benzene, our reagents, the nitric acid and that sulfuric acid catalyst, and our product, nitrobenzene. Again, we need to look at our electrophilic species for this reaction. Okay, so again, we're going to see this reaction between our nitric acid and our catalyst. So we're going to draw our full Lewis structure for that nitric acid. It's going to react with our sulfuric acid. I'm going to be kind of lazy because sulfuric acid here is just playing the role of an acid, so I'm not going to draw the full Lewis structure out. We actually will in our next example in case you're curious, but for right now we're just going to show that donatable proton, make our lives a little easier. All right, and what's going to happen is we're going to protonate. Let me draw it a little differently. Whatever. Protonate that oxygen of our nitric acid. Okay, so everybody take a second, draw me my intermediate. We get this HSO4 minus. But what's happening to our nitric acid here? All right, and once you draw that intermediate, you can then draw our final product, draw the electron pushing arrows to get to our final, what is our electrophilic species here. It's called the nitronium ion. Right, water and the nitronium ion. A little better. All right, so what we have is our nitric acid, but now one of those oxygens has been protonated. And since I replaced one of those lone pairs with the bond, we got this positive charge here. In order to get to my product, water and this nitronium ion, we're going to need to break this bond right here. So we're going to need a bond breaking arrow. So that pair of electrons is going to go from that bond and become a lone pair on my oxygen. But we also need to form our new oxygen nitrogen pi bond here. So at the same time, this pair of electrons is going to come down. And you know what? I'm realizing I've been missing something all along. What's missing from my nitrogen over here? Positive charge. My nitrogen with its 4 bonds needs a positive charge in each one of these steps. My bad. So this creates what we call the nitronium ion. And this is our actual electrophilic species in our reaction mechanism. All right, now for each one of these, I'm not going to continue to do our reaction mechanism over and over again, because again, just like we saw before, it follows our generic reaction mechanism that we laid out at the beginning. You're just going to replace our electrophile here with that nitronium ion. All right, but this will then be my electrophilic species for this reaction. So again, we need a really good electrophile in order for the benzene to play the role of a nucleophile. So we're going to take our reagent and catalyst and react them together to get our nitronium ion. Our next reaction, fairly similar. We're going to again use sulfuric acid, but we're going to use fuming H2SO4. So sulfuric acid that you've heated up to the point where it's boiling and reacting with itself to form our electrophilic species for this reaction. All right, and what this is going to do is put what's called a sulfonic acid group on your benzene ring, SO3H. All right, so again, let's just kind of summarize. It's called a sulfonation reaction. Again, we're going to use fuming H2SO4. We always include the fuming to remind ourselves that we have these specific conditions where we have to keep our acid very hot so it reacts with itself to form our catalyst, or rather our electrophilic species. And we get that sulfonic acid group, SO3H. All right, and we need our electrophilic species. What we're going to see is these 2 molecules of sulfuric acid will react with one another. All right, so we're going to do one where we show all of our Lewis structure here. So this is what we should have drawn in the mechanism for the last one as well, just to show all these bonds, but we got lazy. All right, and then we're going to have another molecule of sulfuric acid playing the role of an acid. So again, we're going to kind of be lazy and just condense this one. I actually decided halfway through that I like this a little better. It's a little bit more accurate of a way to represent it condensedly. And we're again going to do the same thing we did before, where we're going to protonate an oxygen in our sulfuric acid. Right? And you're again going to try to fill in our intermediate here, and then put in the electron pushing arrows for our final step. The formation of our electrophilic species. this thing here. All right, and what we're going to see is our intermediate here, again, just has that protonated oxygen from our sulfuric acid. Okay, in order to get to my product here, am I going to need to put in what type of arrow? Bond breaking, bond formation, or both? So what bond do I need to break? The sulfur to oxygen bond, right? And specifically I want to kick off a water, so I'm going to choose this oxygen right here. But yep, just need that one bond breaking arrow there in order to finish off my mechanism. Okay. What you'll notice that in both this and our last one, our nitration reactions, that sulfuric acid is protonating an oxygen that leads to the loss of water here. So a dehydration of that strong acid, whether it was nitric acid in our previous example or sulfuric acid here, we dehydrate, we remove a water molecule to create our electrophilic species here. Again, this has a fancy name. This is a sulfonium ion. And again, that is our electrophilic species. Cool. All right, so last two reactions to go over here for these EAS reactions. These two are kind of special because they are going to create a new carbon-carbon bond. We don't have a ton of ways of creating carbon-carbon bonds in organic chemistry, and it's always good to keep them in a little bit of a special place in your mind, because instead of just swapping out one atom for the other like we did in this first example, we're going to be creating new carbon-carbon bonds, which means that we're going to be growing the carbon backbone of our molecule. All right? So, first one is going to use an alkyl halide. So R meaning any hydrocarbon chain, right? The rest of my molecule, whatever that is. And a familiar reagent, aluminum chloride. All right, familiar catalyst rather. So this is going to replace that hydrogen with that alkyl group, with that R group. All right, so because these are fancy reactions that create new carbon-carbon bonds, they have a bit of a fancy name. They're named after the chemists that established them. These are Friedel-Crafts reactions, and this one is specifically a Friedel-Crafts alkylation reaction. All right. Take our benzene, react it with some alkyl halide. Okay, and what we get is now that alkyl group attached to our benzene ring. All right, just like before, we're going to look specifically at our electrophilic species. And this one's actually pretty familiar here. So, we're going to take an alkyl halide, pick 2-chloropropane here. All right, we saw this aluminum chloride. We actually looked at aluminum bromide, but same idea. In our halogenation reactions. All right, and just like before, that aluminum is going to accept a pair of electrons from that halogen. Okay, but instead of forming some sort of a complex, it actually just plucks that chlorine off altogether. So this bond breaks at this same time. So my products here are AlCl4 with a minus, and you're going to tell me what my organic product is of this mechanism here following those electron pushing arrows. Okay, we broke that carbon-Cl bond, and we get this intermediate that we've seen before. What do we call these intermediates? I'm missing a charge here. Yeah, so my carbon in the middle lost that pair of electrons, so it forms this electrophilic species we've seen a bunch, are carbocations. Carbocations, of course, lack of electron density, great at accepting pairs of electrons, great at being electrophiles. All right, there is sort of one thing we got to be careful of with these Friedel-Crafts reactions, though, because of these carbocation intermediates. So let's take the example that we just did, looking at that specific alkyl halide with that chlorine on carbon 2. Benzene is going to attack that carbocation. And so what we're going to see is that carbon that had that halogen attached to it is the carbon where my carbocation forms, is the carbon that gets attached to my benzene ring. All right, so specifically here, I would be attaching at carbon 2 to my benzene ring, where that carbocation is going to form. And this should check out. If you did your full mechanism, you would see that, again, that pair of electrons attacks that carbocation, forming that new carbon-carbon bond. But let's take a look at another example here, where we're again going to be using an alkyl halide. But now I'm going to put that halogen over here on a terminal carbon. All right, and if we did this reaction, what we would see is the exact same product as above. As opposed to putting attaching my benzene ring to this first carbon, it still goes on this second carbon over here. So why am I getting the same product for both of these reactions? So yeah, not delocalization, but the rearrangement's what we call shifts, all right? So what we want to ask real quick is why? Let's look at that carbocation intermediate, I'm going to have this carbocation that forms on this carbon. I'll keep my color coding consistent here. I said this one was blue and this one was green. All right, but what do we know about primary carbocations as opposed to secondary carbocations? Are they more or less stable? Less stable. So what happens when we have these carbocations that form right next door to a more substituted carbon is what we call a hydride shift. All right, so my hydrogen and my carbocation are going to swap places in order to create that more stable secondary carbocation. All right, and this is a consequence of every reaction mechanism that has these carbocation intermediates, is we got to watch out for these hydride shifts. And we see these specifically with these Friedel-Crafts alkylation reactions. So we're going to put a warning for this, right? Watch out for shifts. Okay, because these Friedel-Crafts alkylation reactions have these carbocation intermediates, we got to watch out for these hydride shifts or methyl shifts that can occur as a result. All right, so we can just put, actually, just to be clear, hydride or methyl shifts. Always a consequence of those carbocation intermediates. All right, and we have one last one here, sort of similar to before with the previous Friedel-Crafts reaction. This is another Friedel-Crafts, but now using specifically, instead of an alkyl halide, an acyl halide. So we have a carbonyl group in there. We're going to use that same aluminum chloride catalyst. We're again going to see the creation of a new carbon-carbon bond, where we can add any amount of carbons on there we want, but we're going to be specifically connecting at the carbonyl carbon to the ring. All right, so taking that acyl halide and attaching that carbonyl carbon to our ring. All right, this is another Friedel-Crafts reaction, but what's called a Friedel-Crafts acylation. And again, we can have any number of carbons here, but importantly, that halogen is now attached to a carbonyl carbon. So we have what we call an acyl halide. We use that same aluminum chloride catalyst. All right, and what we're going to do is we're going to substitute out that hydrogen for that carbonyl carbon. Okay, so again, another powerful one in that we're creating a new carbon-carbon bond, but important to note that we're specifically creating a new carbon-carbon bond to a carbonyl carbon. All right, and then lastly, same thing, we're going to look at this electrophilic species. we're going to see that that aluminum chloride is doing something very similar to what it did in the previous example, where it's just like straight up plucking that carbon off of there. I'm sorry, plucking that chlorine off of there. So that chlorine attacks that aluminum, but then that carbon just kicks that chlorine off, creating another carbocation, but this one's special because it's located at a carbonyl carbon. Okay, this thing has got a special name. This is what we call an acylium ion. This is, again, our electrophilic species in this reaction. All right, but the good news is that our acylium ion, different from our other carbocations, we do not have to worry about any sort of shifting occurring. It turns out that it's stabilized by that carbonyl position. So we can just say no shifts to worry about for this one. All right, so our Friedel-Crafts acylation reaction, again, we're creating a new carbon-carbon bond, but specifically to a carbonyl carbon. We can have however many other carbons on the other end of this molecule, all right, but importantly, we're forming that bond with our carbonyl carbon. And these are our 6 electrophilic aromatic substitution reactions, where we're substituting a hydrogen for some other group on that benzene ring, all right? So importantly, we're going to use these 6 reactions kind of like over and over again throughout the rest of the chapter. But we're going to start mixing and matching them, right? So if we take benzene and we hit it with our bromine and aluminum bromide, we get bromobenzene. But what happens if we take bromobenzene and do one of these other reactions to it, all right? So we're going to start mixing and matching these. It's a good idea to start practicing just knowing what substrate, or rather what reagent gives you what products, so that when we start mixing and matching these are a little bit more familiar. Cool, but we'll pick up with that next time.